Hi Bobby.
Hi Aniruddhan.
What shall we do this week?
I brought the textbook. We need to.
Excellent idea.
So we need to solve some questions and see how much we have understood.
That is true. I think we have had a lot of theory.
Correct.
Lot of new circuits. No, we
Yeah.
learnt about this transistor
In fact,
and amplifier.
many circuits.
Yes. So maybe we'll do some problems on transistor and amplifiers and things like that. Okay, let us do it.
So I'll maybe there are several questions in this. I'll randomly pick up some.
Sure.
So we'll start with one question. So it says it's an NPN transistor.
Okay.
Which has a beta of 100, alpha of 0.1.
Okay.
And IS is 10 power 15 ampere.
Okay. So, okay. Let me draw this better.
Yeah.
So this is an NPN transistor.
Yeah.
You said beta is 100. Beta is 100, we know alpha, so I think we don't need to worry about that, right?
Yeah.
And you said
IS is 10 power minus 15.
IS is 10 power minus 15 amperes.
And it says the transistor is operated in forward active mode.
Forward active region, okay.
With IB, Bombay,
okay.
10 microampere. And VCB, 1 volt.
VCB is 1 volt,
yeah.
Okay.
Find VBE, IC and IE.
Okay, VBE we want, IC and IE. Okay, perfect. 3 things we need to find out. Okay. So we know IB 10 microamperes.
Yeah.
Oh, so 10 power minus 5 amperes.
10 power minus
10 microamperes, no? So 10 power minus 5 amperes. And let us see. Easy way I can imagine. IC is beta times IB.
Yeah.
So we can find out IC.
Correct.
And then IE is IC plus IB. So beta plus 1 times IB. These two are easy, I think.
That is very straightforward.
This is very straightforward, right? So
for VBE, we need to use the exponential equation.
Use the exponential equation. So 100 times 10 power. So the 100 times 10 microamperes is 1 milliampere.
Yeah.
Right? And IE then is just 1 milliampere plus 10 microamperes. So it's 1.01 milliamperes. Is this correct?
Yeah.
I hope this is correct. I think we have it. Beta, we have used beta and this thing. Okay.
Correct.
Perfect.
One way it's nice. Base current is only 10 microampere, but in the IC you have milliamperes.
Milliamperes, correct. This is a typical operating region, no?
Correct.
For a NPN. Okay, good. Now we need to find out VBE. So this IS is basically IE naught.
Yeah.
I think that's what we have used.
Correct.
The equation I think we have used is IE is some IE naught or IS exponential VBE by VT minus 1.
Yeah.
Right?
In fact, that minus 1 we neglected.
We neglected. In this case, we don't know VBE, so maybe we should not neglect it. We will see. We might have to neglect it.
Okay.
Actually, most likely it will, no, because the currents are quite high,
Correct.
milliamperes.
Correct.
Most likely we can neglect it. Okay. So, IE we know, IS we know. Oh, then it should be easy, no?
Okay.
So, let us see if we can find out VBE. In fact, this is a very useful relation, no?
Log.
VT ln IE by IS is a very common. So, we'll neglect this because, right?
Correct.
We'll neglect it. I'll not write 0. And a very common useful expression to know is that VBE is logarithmically related to IE and IS. So this is nothing but 25.9 millivolts ln 1 into 10 power minus 3, which is IE 1 milliampere, over IS, which is 1 into 10 power minus 15 amperes. So inside the natural logarithm you have 10 power plus 12. So we can evaluate this. So 1 into 10 power 12, we need to take the natural logarithm of this. That happens to be 27.63. You multiply this by 25.9. That gives you 715 millivolts. So this is the base emitter voltage of the NPN transistor. So looks like it is forward biased, but not very strongly forward biased. That is what it looks like, right?
So yeah, I was just thinking this is one way to get ln of a signal also. No?
That is true. You are right. So you are right. If you want to perform the logarithmic operation, you create a current and pass it through a transistor and look at the VBE.
Absolutely
correct. You are right. And you are right. Circuits are built to do this. No?
Correct.
To
electronically get the
log. Correct. And you can use this to compress, expand the signals, things like that. No.
Exactly.
Correct.
Because compression is clear. You have 1 e power
correct
12, that becomes just.
That's correct. That's correct. So I think this is correct, no? 1 milliamp, and this is 10 power minus 15 amperes, no?
Correct. It's
just
amperes.
checking.
Yes.
Okay. Yes. So then this is correct.
Yeah.
Okay.
So we'll pick another one.
Let's pick another one.
PNP.
Sure. That's interesting because we have not done any PNP so far.
Correct.
Sure. Let us do a PNP.
So it's a PNP transistor.
PNP transistor.
IS. Okay.
So what I will do, I will just for students' reference. PNP transistor. Let's show the direction of the current.
Yes.
Because that is slightly different, no? So IE flows into the emitter from outside. Collector current flows outside like this, and base current also flows outside. So exactly opposite. And the equation is IE is IS exponential VEB by VT minus 1. Right? Okay. So this is just for the students' reference.
So the IS.
Oh, by the way, I forgot to realize one thing. The students may be wondering why VCB is given, right? You need this to show that it is in forward active region, right? So because it needs to be reverse biased.
Correct.
So you need to ensure that it is reverse biased. That is why.
But actually the question also says that it is forward.
It is forward active region. So it is just extra information. Correct. Correct.
But if that FAR was not mentioned, then we could find out from this voltage.
Correct. Okay, please.
So the IS is 10 power 13, minus 13.
10 power minus 13.
Ampere. Beta is 40.
Beta is 40.
Emitter is connected to ground.
Emitter is connected to ground, okay.
And the base is connected to a current source.
Okay.
That pulls 20 microampere out of the base terminal.
Okay, so I'll show those connections outside. So 20 microamperes, Okay.
And the collector is connected to a negative supply of minus 10 volt.
Minus 10 volts directly or through a resistor?
Through a 10 kilo ohm resistor.
Oh, perfect. Okay. So minus 10 volts, and 10 kilo ohm resistor. Oh, okay.
So the question is to find collector voltage, emitter current, and base voltage.
Collector voltage, emitter current, base voltage.
Correct.
Okay. So I think let us see how to approach this problem.
Base current we know.
Beta we know.
Is not.
So automatically IC and IE we know.
Correct.
Right. In fact, this is a very common way. No. Once you know beta, and you know or alpha and one of the currents, you can find out the others. In a transistor. That's a nice thing about the BJT. Right. And beta is a pretty common transistor property. Okay, so this we can find out easily.
Yes.
So since they have said IE, so IE is just beta plus 1 times IB.
Yeah.
And that is simply 41 into 20 microamperes.
Yeah.
This is 820, sorry, yeah, 820 microamperes. This is IE.
IC is just
IC will be for 800 microamperes.
Correct.
Okay. Then, since we know IC, we know VC collector voltage.
Correct.
It is minus 10 volts plus IC times 10 kilo ohms.
Yeah.
VC is minus 10 volts, that is the potential here.
Yeah.
And then you will have a potential drop here.
Correct.
Of IC times 10 kilo ohms.
So that 800 micro into 10 kilo ohm.
Plus 0.8, I'll say 0.8 milliamperes into 10 kilo ohms.
Yeah.
So milli and kilo will cancel. 10, it's 8 volts. 8. So this is minus 2 volts.
2 volt.
So the collector is at minus 2 volts. So
yes.
This is 1. IE is 820. Okay.
Next is VB.
VB. To do that, we need to solve this, I think. If you want to find out the base voltage,
we need VEB.
You need VEB, so you need to solve the current equation. So you need to solve this equation. Why don't we do that? So I think last time also we saw.
Yeah, so in a way it's similar to the previous question.
It's very similar to the previous question actually.
Yeah.
Except it's for a PNP. Correct. The directions are all opposite.
So, VTLN. Yeah.
Right. So this is
IE we know 820.
So, yeah.
So this 25.9 we have to memorize.
Yes.
Most of the questions are not revealing.
Most of the questions are not revealing it. KT by Q, Boltzmann's constant, absolute temperature, electronic charge. They are all fairly fundamental. You assume it's room temperature.
So if I remember as 26 millivolt, it's okay.
26 millivolts is easy to remember. Yeah. In fact, for most engineering applications, 26 millivolt is good enough.
Yes.
If you are doing some precision application, you will need probably 3 decimal places anyways.
Yeah.
Right?
Yeah.
So
820 by IS is 10 power minus
30. Okay. So 0.82 milli by 10 power minus. So 0.82 into 10 power 10.
10. Yeah.
Right. So maybe we can just do that now. Shall we do that?
Yeah.
So 0.82 into 10 power 10, and we want to take the ln of this,
yes, no? Ln.
It's 22.83.
Okay.
And we multiply this with
25.9.
25.
Correct.
591 millivolts.
Yeah.
Okay. 591.23. I think in the exams we ask them for 2 decimal places, so we'll write it to 2 decimal places.
Yeah.
Okay. So I think.
Also, we are done.
We are done.
So is this in forward active?
We need to check that, no?
Yeah.
Because we have used this, we need to check whether it is in forward active.
Yeah.
So VEB is this, which means VB. Actually, we have not solved for VB yet. Emitter is at ground.
Correct.
So VB is at minus 0.591.2. Yeah, minus 0.591.
Yeah.
Millivolts.
Yeah.
Sorry, volts. So this is negative. Now we need to look at VCB. Right. So
minus 2.
It is PNP.
Correct.
Right. So the N voltage we said is at minus 0.6, I'll say.
Yeah. Yeah.
we said this is at minus 2.
Yeah.
So the P is more negative.
Than
so
N.
it's than N. So it's reverse biased by 1.4 volts.
Yeah. So
So
that junction is fine.
That junction.
The other junction?
The other junction by definition is forward biased. Emitter is higher, base is lower.
So
great. So I think this is good.
Yes.
Easy problems. One page solution, right?
But gives good understanding of.
Very good understanding of how to solve the problem. You are given
Correct.
2 things, find out the others.
Correct.
Right. The BJT is very nice because you only have to remember 2 things, no? One is this exponential equation, the other is beta relationship.
Yeah.
That's all.
So now we will pick. So I have a PNP again.
Okay,
And,
I see. Maybe I'll just look at it and draw it.
Yes.
Okay. So I have a resistor and this is ground.
Yeah.
And this is plus 10 volts.
1 kilo ohm.
1 kilo ohm, 1 kilo ohm. And okay. And I have a resistor like this, 100 kilo ohms.
Yeah.
And basically the question is saying,
measurements on circuit.
Okay. So maybe I'll show 2 voltmeters.
Yeah.
Like this.
Yeah.
I'll show 2 voltmeters like this.
Correct.
So V1
is
and V2.
Yeah.
I'll show it like this.
Correct. So V1 is 6.3.
V1 reading is 6.3 volts.
V2 shows 7 volts.
7 volts. Okay.
If so, what is beta?
This is a PNP, no?
PNP.
PNP. Okay. We want to find out what is beta. Okay. So first of all, a voltmeter reads the voltage at any node without changing that voltage.
Yeah.
So it doesn't draw any current.
Ideal voltmeter.
Ideal voltmeter,
Yeah.
right? So I think that is the first assumption. In case students don't remember, we will say this. There is no current here.
Yeah.
Right? So that is something they need to
Correct.
So, okay.
So, IE we can find out.
IE we can find out because we know VE. Right? So if this is VCC, IE is nothing but VCC minus VE by this resistance R.
Yeah.
So plus 10 volts minus VE by 1 kilo ohms. VE is nothing but 7 volts.
Yes.
So this is 3 milliamperes.
Correct.
That is the emitter current. IE. Okay.
Now
we don't know beta.
we don't know beta. That's the question.
That is the question, right?
Somehow we need to find out base current. Huh?
Correct. So brute force way, if you do it, there are only 2 unknowns, which is collector current and base current.
Oh.
Right? So the brute force, if I were to think of it, I have 2 unknowns.
Yeah.
Right? And I know one relationship, which is IB plus IC is IE.
Yeah.
So that is one relationship I know, which is IE is 3 milliamperes.
Yeah.
The one relationship I know. The second relationship I have to make by applying KVL, KCL. So for example, this is base current and I know that the base current flows like this.
Oh, because anyway it is not going
It is not going through the voltmeter.
Yeah.
Right? So it has to come through the 100 kilo ohm.
Yeah.
And then it adds up and flows through the 1 kilo ohm.
Correct.
Nice thing is, if it adds up, IE flows here. Correct? So I know that this voltage, because it's base current. I know that IB plus IC is IE.
Yeah.
And that is what flows through this 1 kilo ohm.
Yeah.
So I'll just write it as IB plus IC. But we know that this is 3 milliamperes.
Yeah.
Which means that this collector voltage, VC, is 0 plus 3 milliampere time 1 kilo ohm.
Yeah. 3
volts.
Yeah.
Okay. Now it is straightforward. I think we can calculate IB.
Base current we can.
Base current we can calculate. So IB.
3.3.
So it is basically
6.3
yeah,
minus
VB minus VC by 100 kilo ohms.
Yeah.
So VB is 6.3 minus 3 by 100 kilo ohms. Is this correct?
Yeah.
So this is 3.3 into 10 power minus 5.
Yeah.
33 into 10 power minus 6.
Microampere.
33 microamperes.
Yeah.
Now it is easy. IC we know is so 3000 minus 33, which is 2967 microamperes, 2.967 milliamperes.
Beta.
Beta we need. Beta is IC by. Actually, once you find out IB,
Yeah.
it is 3 by beta plus 1.
Correct.
Easy, but yeah. So 2967 by 33. So let's find out what that is. 2967 divided by 33. 89.91.
90.
90. Correct. Yeah, you will never have this level of accuracy for,
For
beta in any measurement. So, okay, this was a nice problem.
Yeah.
Right. I think there were two things. No, important thing to realize is that the question said you are measuring the voltage.
Not it's a voltage given
It's not a
to
voltage
the
given to the circuit. So you have to maybe that part was a little bit hard to understand.
Yeah.
Right. But once you do that, you also have to assume it's an ideal voltmeter.
Correct.
So current is 0. Everything else was easy. So I think a lot of these seem to, you use transistor equation and then KVL, KCL.
Yeah.
You can solve the problem. No?
Basic algebra only.
Basic algebra only. In fact, this is slightly easier also compared to phasors and all where you had complex numbers.
Correct.
Right? Even the algebra is easier.
Correct. And compared to Laplace transform.
Compared to Laplace transform, it's much easier.
So now we will take something where we apply plus and minus VCC.
Yes, sure. Let's do that.
So I have one like that here.
Okay. Okay.
NPN transistor.
NPN transistor this time. Okay. So I'll draw the circuit.
In the collector and emitter, we have 10 kilo ohm.
10 kilo ohm. So, and it's plus 9 and minus 9.
Yes.
Okay.
In the base, from the base to ground, there is a 10 kilo ohm.
10 kilo ohm resistor. Okay. And do you have any voltage here or something?
No, it's just marked VB, VC and VE. Let me see what's the question. Oh, so it says that they have done some measurements again.
Okay.
VB, Bombay, is minus 1.5.
Okay, minus 1.5. Okay.
And it says assume VBE is 0.7.
VB is 0.7.
Yeah.
Okay.
If so, calculate
VBE or VB?
VBE.
Oh, VBE is 0.7.
Yeah.
Okay. Okay.
Calculate VE, alpha, beta, VC.
Okay. Similar problem, little bit similar problem to last time. So, okay. So this is ground, right? The 10 kilo ohm is grounded.
Ground.
Okay. Okay. So we will start with the same assumptions last time. This current was 0. Correct. So we can find out
base current.
Right? So base current is going to be
1.5 by 10K.
Correct. 1.5 by 10K. So no, base current is flowing the other way, of course. I don't know why I drew it like this, because we have a negative current, right? So base current has to be flowing the other way.
But value is correct, no?
Value is correct.
Yeah.
So I'll just show it correctly, because the minute you know the base voltage is minus 1.5 and this is 0, current has to be flowing like that.
Yes.
So value is correct. 1.5 divided by 10 kilo ohms. So that is 150 microamperes. Is that correct? 0.15 milliamperes.
Yeah. Correct.
Okay.
VBE is given. So that way we can find out VE directly.
That is true. That is true.
So it's minus 1.5 plus 0.7. No?
Correct.
Or the
minus 1.5 minus 0.7. No?
Minus 0.7.
So the emitter voltage is 1.7 volt below the base voltage.
Correct.
So minus 2.2.
Correct.
Okay.
Also VE is VE we have. Then
VE
what else
we
we
have?
want?
We
Alpha,
want
beta.
alpha, beta, VC. To do that, we need to find out the currents. Oh,
10K. So
10K. So this is IE and this is IC.
yeah.
So IE is going to be VE minus 0.9
Yeah.
divided by 10 kilo. So VE we found out.
Correct.
So
6.8.
6.8. Which is 0.68.
Milliampere.
Yes.
IB we know.
So we can find out beta
Correct.
right now already.
Yeah.
IB we know. In fact, we know beta, we can find out everything now, because we know two of the currents.
Yeah.
So IC is going to be IE minus IB. 0.68 minus 0.15 is 3.53. Is this correct?
Yeah.
So IC we know. So if IC is known, VC we can find out.
Or we'll find out alpha first.
We'll find out alpha first.
Or beta.
Or beta. Let's find out beta. Beta is 0.53
by 0.15.
by 0.15.
Not so nice numbers.
I know. 0.15. No. Sorry. 0.53 divided by 0.15. 3.5. Very, very small beta.
Yeah.
Right? So the numbers are correct. This is 10 kilo ohm or 100 kilo ohm?
Let me see.
The base resistance.
10 kilo.
10 kilo ohm. All three are 10 kilo ohms?
Yeah.
Okay. And plus 9 volts, minus 9 volts, no?
9 volt.
Okay. So looks like a very, very small beta. So beta was only 3.5. I mean, that's clear when we calculated IBM.
Yeah,
right?
I was thinking we made some mistake.
Very surprising.
Because once we have base current of 0.15 milliampere,
Correct.
collector current we expect large.
Much larger.
That was not happening.
Correct. So beta we know.
Yeah.
And alpha is IC by IE. So by 0.68. Point 0.78.
Yeah.
Okay, it's very small alpha, no?
Ideally, it should be close to 1.
It should be very close to 1. We saw when beta is 100, alpha was like 0.99 or something,
correct.
no? So, not surprising. Okay. And
Next is VC.
VC.
IC we know. So
we know IC, we know 9 volts, we know 10 kilo ohms.
Yeah.
Easy. Vc is plus 9 minus IC times 10 kilo ohms. So so 9 minus 5.3,
Yeah.
which is 3.7, correct? 9 minus 5 is 4, 4 minus 0.3, 3.7
Yeah.
volts. Okay, so this is good. So you are able to find out everything, VE. Same idea, no? So voltage you measured, find out what you measured, KVL, KCL plus transistor equation.
Good.
So any other problems you wanted to solve?
Maybe some.
Maybe this one we have done in class with NPN. Shall we try it with PNP?
Yeah, we can. We can.
Okay. So that is problem number. Okay. Maybe on the previous page. Okay.
Yeah, 3.3. 3.3 kilo ohm, 5.1 kilo ohm, and the base resistors are
And what is the supply voltage? Plus 5 and
plus
minus
5
5.
and minus 5.
Okay, and the two, okay, you have two resistors on the base.
Yeah.
To bias the, and they go between the two supply
same
voltages.
Top one is 91 kilo ohm, bottom one 150 kilo ohm.
Okay.
Then some node voltages are marked. V10, base is V10.
V10, V11,
and V12.
V12. Okay.
I think the question is actually to find out the values of the voltages.
These three voltages.
These three voltages.
Okay.
And branch currents.
And the branch currents. Okay.
Assume beta to be very high.
Okay, that makes our job a little bit easier.
And VBE is 0.7.
VB. In this
Raised
case,
to
VEB.
emitter. Yeah.
In this case, VEB.
Yeah.
Okay. So VEB is 0.7 and beta is large. We basically want to find out all voltages and currents.
Yeah.
Right?
Beta very large means no base current.
No base current. Right? So
V10 is easy.
That is easy. Right? So this is almost equal to 0.
Yeah.
This is what we assume. So this is 0.
Correct.
Then it is easy. V10 we can find out. Is 150 by 191 times difference between the two voltages plus minus 5, right? That's the way to do it, no? Or which way shall we do it? So minus 5 plus, so I guess I'll write it maybe the full this thing way. We'll write it the right way. I'll write it like this. So you have minus 5.
Yeah.
So we'll write it like that. Minus 5 volts plus 150 times the current. Correct? So you have some current, some, what shall we call it, some Ix or something. So Ix times 150. Right? We'll start writing it like that.
Okay.
And Ix is plus 5 minus 5
by total resistance.
By total resistance.
So basically apply superposition and find out.
That is correct, the best way to do it. Correct. Okay. So what I started off doing at the beginning was writing it as 150 by 91 plus 150 times the difference between these two voltages plus minus 5. So same idea, but better to do it full. We are after all solving from scratch, no?
Correct.
Better to do it in the first principles.
Yeah.
So this is Ix basically. This is Ix. This is correct, no?
Correct.
Okay. So as you said, superposition will definitely give you the answer, right? So 10 divided by 241.
Yeah.
Okay, we'll just do that. So 150 plus 91 is 241. So is there a
1 by
x is there? 1 by x into 150 into 10. So
kilo will get cancelled.
Kilo will get cancelled. So
6.2.
So this portion is 6.2
plus
6.2, and then you get minus 5. So maybe I'll just mark that. So 6.2 volts. We'll just, in these examples, we'll just truncate to the first decimal place.
So it's 1.2 volt, is it?
Yes, 6.2 minus 5, 1.2 volts. So this is the first voltage. VEB is given.
So if both resistors were equal, it would have been 0.
It would have been 0, correct. If you had 150 and 150, it would have just been 0, correct. It would have been exactly halfway.
Correct.
Superposition.
So top resistor is smaller, so it will be pulled a little bit positive side.
Little bit positive side.
So it's correct.
It's correct.
1.2. Oh, so now V11 and V12.
V11 and V12. So I am thinking VEB is given, no? So we know VB. So V11 we can find out.
Yeah.
That is correct?
Correct.
VBE. So V11 is V10 plus VEB. PNP transistor. So emitter is at a higher voltage compared to the base. So this is 1.2 plus 0.7, which is 1.9 volts. So V11 is also known. By the way, we wanted to find out all voltages and all currents, right? So I'll just that was our requirement. Okay. So V11 we know.
Now IE also we can find
IE also we can find out. IE is 5 minus V11 by 3.3.
Yeah.
.9 by 3.3 kilo ohms. 5 minus 1.9 is 3.1 by 3.3.
Should have been 3.3.
Yes. Point
939.
Yeah, so 0.94 milliamperes. And beta is large, so that is IC as well.
Yeah. So IC into 5.1
plus minus 5 will be V1. So where can I write that? I need to write only that, so I'll write it in blue. So this voltage, I'll write it here, is minus 5. Okay, wait. We'll write it here.
Yeah.
I'll create some space for myself here. V12 is
minus 5 plus IC into 5.1 K.
5.1 K. So this is minus 5 volts plus IC is 0.94 into 5.1. which is, I think we need the
Correct,
calculator. So 0.94
into 5.1.
5.1. This is 4.79 plus minus 5.
Minus 5.
Minus 0.2. Okay. Okay. Now we know all the currents and all the voltages in the circuit. We know Ix, we know IE, we know IC, IB is 0. We know all the voltages.
Nice.
Okay, nice. Again, straightforward application of KVL, KCL with around the transistor.
Correct.
With beta equal to large is what we did.
Yeah.
Okay, nice. So, Bobby, what shall we do next?
We'll do one current mirror problem.
Sure.
So, I have one here. So, we'll draw a basic current mirror. I'll give the numbers.
Okay.
So, we wanted to generate a current of I naught of 10 microampere.
Okay. So, you want to generate an output current of 10 microamperes.
Yeah.
Okay.
I have 10 volt supply.
Okay. You want to create the current using a resistor. Okay.
Resistor R1.
Some value R1. Okay. And do you know the beta of the transistors?
Actually, determine the value of required resistors, assuming that VBE is 0.7 at a current of 1 milliampere and neglecting the effect of beta.
Okay. So, beta is large.
Yeah.
And you are also told that VBE is 0.7 if when the current is 1 milliampere.
Yeah.
Which means if you expect this VBE to be less than 0.7 because the current is 10 microamperes, much smaller. So, we can't use VBE equal to 0.7.
Directly.
Otherwise, it would have been easy, no?
Correct.
Okay. Okay. So, Q1 and Q2 are identical. So, we'll assume that this current also is 10 microamperes.
Actually, we have to pass only 10 microampere there to get 10 microampere here.
Exactly, correct. Otherwise, you could maybe make the area of the ratios different, but we will not do that, no?
Correct.
That is more complicated. Correct.
Assuming that Q1 and Q2 are identical.
Q1 and Q2 are identical. And we also said that beta is large, so this base current is 0.
Neglected, yeah.
Neglected.
Yeah. So,
and we don't know VBE.
Yeah.
So, now.
So, what will be VBE if the current is 10 microampere?
If the current is 10 microampere. Correct. We don't know IS.
No.
We don't know IS. Oh.
Earlier we used some expression for VBE, no?
Correct. Correct. So, VBE, that is in terms of IS.
No, some VT, ln.
IE by IS.
Yeah. Oh, IS is required.
But maybe we can find out IS from this.
IC we know.
Correct.
Okay.
Maybe we can find out IS from this.
From that.
Correct. Shall we try it? Okay. So, let's start by writing down this equation that you pointed out. VT ln IE by IS. In this case, beta is large, so IE is IC.
Yeah.
So, that doesn't matter.
Yeah.
So, I'll say this is correct, no? So, I'll say, yeah, is IE, right? So, maybe what I will do, I'll say this is VB naught and IE naught by IS.
Yeah.
Yeah. And we want to find out the new VB1.
Correct.
Is VT ln 10 microamperes, right? That is I naught. So this we know is 0.7.
Correct.
So suppose I subtracted the two equations, Vt ln Is will get cancelled. Okay, try that. So this is 1, this is 2. I'm going to do 1 minus 2. So 0.7 minus VBE1
Correct.
is, so I'll get Vt ln IE naught
By I naught.
by I naught, because I'll get minus Vt ln I naught. So we'll just write it like that, right? So this is 26 millivolts into ln of IE naught is 1 milliampere,
Yeah.
by I naught is 10 microamperes.
Yeah.
This is 100, no?
Yeah.
So we need ln 100 into 26. 120 millivolts. We're just going to round it to the nearest, closest integer.
So that is
0.7 minus VBE1.
Yeah.
Right? So VBE1 is 700 minus 120, 580 millivolts. Okay, so that is this voltage
When 10 microampere is flowing.
when 10 microampere is flowing.
Oh, so now we can find out what should be the value of
What
R1.
should be the value of R1? So now R1 is going to be 10 volts minus VBE1 divided by 10 microamperes. By 10 microamperes. So 10 minus 0.58 is 9.42 divided by 10 microamperes. Okay. Oh, we don't need a calculator for that. 9.42 divided by 10 power minus 5.
Yeah.
So 9.42 kilo ohms.
Yeah.
Approximately.
Yeah.
9.42 into 10 power 5. 942 into 10 power 3. Okay.
That is value of the R1.
That is the value of R1. I think that is what they wanted now.
Yeah, correct.
Okay.
So that's it. Once we connect that, there will be 10 microampere flowing. Same base voltage is given to the other one.
Correct.
So the I naught will be same.
Correct.
Because the transistors are same.
Correct. And I guess if beta were not large, this problem will get very complicated, no? So
because we cannot neglect that current.
We cannot neglect that current. The equations will not be so easy. So it will become very complicated.
Nice. So we'll take another problem.
Sure.
Oh, I have some circuit like this.
Oh, okay.
So the question is, if this current is this, what is this current?
Okay.
We'll draw.
We'll draw it. Okay. This is a nice. Okay.
One transistor is connected to the back of the other.
So, correct.
Base of the other.
Correct. So I'll draw it. You tell me whether I'm drawing it correctly.
Yeah.
This is correct.
Yeah.
And
that is 10 microampere. Sorry, milliampere.
And the supply is VCC.
Yeah.
And
so
I think this is Q1 and this is Q2.
Q2. It says beta is 100.
for both transistors.
Yeah. If so, what is the base current of?
Okay. So we want to find out IB1.
Yeah.
Okay. Nice. Okay.
Maybe we'll find out IB2 first.
Correct. So let's find out IB2 first. So IB2 is IE2 by beta 2 plus 1.
Yeah.
So this is 10 milliampere by 101.
Yeah.
I mean, maybe it's a good idea to just, we'll calculate it exactly.
Correct.
10 divided by 101. So this is 99 microamperes.
Yeah.
If it were 100, we'll get exactly 100 microamperes.
Correct.
Right? Okay.
So this is the emitter current of the Q1.
Okay. Correct. This is IE1. Correct. Which means now IB1 we can do the same expression. Nice.
So once again divide by 101.
Divided by 101. Correct. So it is IE1 by beta 1 plus 1. And that is 99 microamperes divided by 101. So 0.98 microamperes. Oh, this is very small.
So from 10 milliampere, it has gone to 0.1. Sorry,
Correct.
1
microamperes. So that is almost 10,000.
Yeah.
Right?
So it is equal to having one transistor with huge beta.
Correct. So that's what it seems to look like, no? So across these three terminals, right? So this seems to be equivalent to almost some new Q3.
Yeah.
So the base current coming out of this terminal is 10 milliamperes.
Yeah.
The current going in is sum of the two currents, right? That is not a problem. And the base current going in is very close to 1 milliamperes.
Yeah.
1 microampere.
1 microampere. So it's almost beta 1, beta 2.
Correct.
Because here both betas are same, it's beta square.
Correct, almost beta squared. Correct. Nice.
So
have they given a name in the question to this?
So it says Darlington follower.
Okay. I see. Okay.
We will write it there.
We will write it there.
Darling anyway they know.
Correct.
So just Darlington.
Darlington. I see.
So this is a very nice way to reduce the base current.
Reduce the base
if you don't want to draw current from the.
Correct. From the circuit.
Yeah.
Correct. In fact, I have seen one small variant, I think now that I remember. I have seen some variants where they add a small current source here also. Things like that. But the idea is the same. Inside it, sometimes they add a small current source there.
Why they add that?
Mainly because you want to, the two betas may not be equal. Because this bias current is 10 milliamperes. This bias current is only 100 microamperes. So the betas may not be 100. One beta may be 100, but the other one may only be 50.
Okay.
So you want to make them both 100. You can now also want to bias this close to not 10 milliamperes, but maybe
operate both in almost the same
correct
conditions.
Correct.
But that's beyond scope of this course.
That is definitely beyond the scope of this course.
Okay.
Correct. So anyways, a nice circuit. Darlington pair.
So this is a differential pair, differential circuit that we discussed.
We'll do that next.
Yeah.
Okay.
In fact, that can have Darlington pair as input.
Yes, it can.
Yeah.
Why not? Why not? You want to do it that way?
No, I'm just
So
asking.
it will get very complicated, but yes, of course, what you are saying is right. So I think it looks like
If I want to increase the input
impedance,
or
reduce the input
not
current.
to draw any current from the source.
Correct. So in fact, looks like this thing can be used anywhere where you want to make a super transistor. No, almost.
Exactly.
It looks like that. So you can use it any circuit where you are using a normal transistor. It looks like you can do this Darlington pair.
Looks like a Superman.
Correct.
Equivalent.
Correct.
Okay. Differential, we will make our own one.
We will make our own question.
Yeah.
Correct. Because we have done a lot of textbook questions. We'll make our own.
Correct.
So what circuit do you want to build?
We will draw and give
Let me draw the simple differential pair that we did yesterday. Okay, so and shall we put a current source?
Yeah. Maybe 1 milliampere.
1 milliampere. Okay. And VCC, what shall we do ground, or you want to do? Shall we make the problem interesting?
Yeah.
We'll apply some other different condition instead of doing simple analysis. We'll say like this. So let us say we have plus 10 volts, and we'll say that we have minus 10 volts.
Yeah.
And we'll say that we want to first of all make the output DC 0 volts. Shall we try like that?
Okay.
Let us see what that gives us. I want to make
individual
voltages should be 0 volts.
VC1 and VC2.
VC1 and VC2 should have a DC value of 0 volts. So I think we called it the common mode value. We want that to be 0 volts. We'll put that as one of the conditions.
When there is no signal applied.
When there is no signal at the base of Q1 and Q2. Shall we make it interesting?
So that means RC we have to select.
We have to find out RC.
Okay.
Correct. So as usual, Q1 is identical to Q2, and what we'll say is VO1 and VO2, no?
Yeah.
So we'll say 0 volts if
what should be the RC for this?
If a small VB1 and 2 is 0, right? No signal. We still need to give DC.
Correct.
Right?
Correct.
Okay. So this is one condition we will put. And we need to give maybe one more condition.
Beta we will assume large, or?
Beta will assume large.
Yeah.
That is easy. I think maybe we'll put one more condition. Maybe something simpler. What shall we say? Shall we say put a condition on this voltage? What shall we do? That is easy. But we need to.
I wanted to know what is the maximum input I can give.
Okay.
And still in
forward
active region.
We'll do like that. Okay. So I'll say input, no?
Yeah.
VI1 equal to is maximum value something like this.
Yeah.
Okay, we'll do that. So this is what we are giving here. VI1.
Yeah.
VI2. Right now no signal. So that's why small VBE 1 and 2 are 0.
Yeah.
Right? So DC. Everything is DC right now. Okay. So how do we start?
First one we will find out what is
First one we'll find out.
What
I think
is RC required to
RC required. That is easy, no? So this tells you that plus 10 minus 0 divided by RC should be the current. So first step we need to do, this is 1 milliampere. So the current through each one is half a milliampere. Right?
So across RC there should be 10 volt drop.
10 volt drop. Correct. Correct. So we know that 0.5 milliampere times RC should be 10 volts.
Yeah.
So RC is 10 by 0.5 is 220 kilo ohms. Easy. Okay. So that is one condition, easy condition. One step, no? Output you know the bias current, operating point current, so you know this. Perfect. Second one, not so easy, right? So what do you do?
We know.
You said maximum value. So what does that mean? Are you telling me that if I increase, you said this question, right? This part. So what you are saying is,
if we keep on increase, this the collector base will become forward bias at some point. No?
Correct. Oh, that is true. Because the current is staying, this is the current source. So the currents are always 0.5 milliamperes. And the collector voltage is constant.
Correct.
So when this increases, this is constant at 0 volts. I like this question. Nice. I like the question that you have set. Right? So the collector voltage is constant. The base voltage keeps increasing. So collector base junction will eventually go from reverse bias to zero bias to forward biased. So you want to find out the point when exactly it is zero biased?
Yeah. Okay. Because beyond that, if we give an input voltage, then it's no more the amplifier that we are expecting.
That is true. That is true. Okay. So how shall we write this condition? So this maximum, we said that the collector base junction is zero biased. So VCB is 0.
Yeah.
We know VC.
Correct. Now the solution is easy.
Solution is easy once you recognize this.
Yeah.
So maximum is just 0 volts. No?
Yeah.
Easy. Easy. Okay. Again, one step, but important to recognize what is happening in the circuit. Nice question.
So this means I can not give any positive signal.
Correct. In this circuit. Because we put the first condition.
Correct.
If you didn't put the first condition, you could choose something, right?
Yes.
Correct.
So now let's say if I want to go up to positive 2 volt or something, then accordingly this RC will have to be adjusted.
Correct.
Then of course the first condition
is gone. You will have to in fact reduce RC, right? We can do that. Yes. So then that, suppose you want 2 volts, no? VI1 max should be 2 volts. Then what will happen? VO1 and VO2, so you need an 8 volt drop across RC, which means it will be 8 by 0.5. Instead of 20 kilo ohms, you need 16 kilo ohms.
Correct.
Correct.
So the gain, the GMRC, that will reduce.
That will reduce. Correct. That's correct. And if you want to increase that, you'll try to increase the current to increase GM, but then the voltage will drop.
Correct.
So this is not so straightforward circuit to easily make that trade-off.
So it's a question of input swing.
Correct.
And
the
gain. Correct, no?
That is right. Nice problem.